I'm Giulio Alessandrini. I'm working in the image processing team, mainly on neural networks and color processing. And today I'm indeed talking about colors. My talk is playing with colors. Good morning. I'm Giulio from the image processing team, and I decided this year not to have the typical talk of the last couple of years in every conference that was about machine learning and neural networks on images, because I mean there are more of them, and you've probably attended them here and there also at this conference. So I say, why don't we go back to basics? And this is something that we have been in various degrees having in the language since a long time. There's some new stuff, some old stuff, but I never really presented comprehensively this topic of colors at this conference. So I said, like, why not? Let's do it. And so the idea is to yeah, sure. That's a very good idea. This or more? More? More. Who wants more? 150? 151? Okay. So the idea is, like, let's start from the basic. What is a color? Like, we use them, we have images, we have all this kind of convolution layer, extracting properties, classifying, localizing things, transfer style, but like, in the end, we are displaying something that we see. So what's behind a color on a screen? I mean, what actually is a color? I think that almost everybody here from a sort of scientific background, even a little, can say that color is light. It's electromagnetic light that just is emitted or bounces against something and then reaches your eyes. And we have sensors here. Like they're organic, but still sensors. So we see, according to the frequency the incoming frequency, we see different things. Oh, this is not in scale, of course. It would be like pretty difficult to see the difference. But I mean, the idea is like lower frequencies we associate with colors like red or like blue, and then or green. Then we move through like this kind of bluish green, and then we have blue, and then we have violet, which is not in this spectrum, but trust me. And then it disappears. I mean, above and below, because we cannot see. Our sensor doesn't work. So here I put, like, for the physics inclined, like this is the formula for the energy of a photon, and like, okay, omega is just a rescale frequency. So like it depends according to the Planck constant. The energy is directly proportional to the frequency. So like we see more energetic light as blue and less energetic light as red. So the idea is that we associate what is called like visible spectrum to the frequency, or like I started with frequency because it's directly proportional to energy, but like actually what we use typically in color science is we talk about wavelengths of colors. So when you say that the length of light is something, it refers to this. So like bigger wavelengths is like red, lower wavelengths is green, blue, and violet, like higher energetic. And you can see like this all experiments that you can do. Like if you take a prism and you shine white light, it split according to the frequency. So you see different colors coming out. So this is the classical experiment to show you like the white color is made of colors of different frequencies. And so, but why? Okay, dynamic. But not everything emits light on its own. So like when we actually see colors from objects, we are seeing reflected light, and the light that is reflected is generated by something else. This something else, typically outside before the technological era, was the sun, and it's still the sun for like most of the time. So like we need, if you want to understand how these colors are produced, we need a model for the light which is emitted from the sun. And the classical model here is to use a simple black body radiator. You may know that every like substance emits light according to its temperature, following a law which is this one. And the nice thing about this law is very simple, because the amount of light that you emit at every wavelength is only depending on your temperature. So like we as a human being, we also emit light. We cannot see it because it's an infrared light, and our sensor in the eye, it doesn't work. But if you use an infrared camera, you can easily see human beings shining. And your phone emits light at a different temperature. It's very cold, so like it's even lower temperature. And other things emit at different frequencies that we may or may not see. So basically, this is a representation of the emission spectrum of a black body. Like for each wavelength, you have the emitted energy. And you see that if I vary the temperature, you have the average color there, given the temperature. And then you see that like I painted that black where we don't see it, and then I put real colors where we can see them. And you can see that as I move, the peak of emission changes. And actually, our sun temperature is around 6,000 Kelvin. It's a little less. And it's not by chance that what we can see in terms of wavelength of light is exactly around the peak area of emission of the sun. I mean, nature is not dumb. We have optimized our sensors to see what's actually is hit by the most electromagnetic radiation from the sun. And so basically, this is how like light comes to be and comes to us. I wanted to have a little experiment here because Eduardo, the colleague of mine, asked me something like 2 weeks ago. As like, I want to do the classical calculation about what's the color of the sky, and it didn't turn out. So we look at that together, and I asked him permission, so I can show it to you here. So basically, we can use what we just seen to just perform a simple calculation. For example, I can get from let's hope it's work. Internet works. No. Okay, so I can query for the temperature of the sun, which, as you see, is like roughly 6,000 Kelvin. And then I can, oh, sorry. This is, I need this. No, I don't want satellite because I want to pre-compute the function given the temperature. So I want to remove the temperature dependency, just we shine the sunlight, and we just want the dependency on the wavelength. So we define this formula, and then this is what we tried at the beginning. Yeah? So like you get what's the average frequency that arrives to Earth basically, and that's pretty low, and unsurprisingly, sorry, it's a wavelength. Unsurprisingly, we don't see that, but that's a very like stupid calculation. We just want to restrict ourselves to the stuff we can see. So we check online, and the typical range of visible light is from like 400 nanometers to 700. So if we try to integrate that, we get a different wavelength, and we get a different color, which is disappointing. I mean, I don't know if you can see that, but it's not the color of the sky. But then that's a catch. Like the light of the sun is indeed this spectrum that we have seen above here, but then it hits the atmosphere. And in the atmosphere, you have a lot of air and things. And if you're a physicist, you know that there's ray light scattering happening. So we need to change a bit the spectrum of the light to take this into account. And because we want to measure actually the diffused light from the particles in the atmosphere. So we divide by lambda to the power of 4, which is roughly the how do you say the order of the ray light scattering, and we try this integral again, and now we get much better color, I would say. So it works, and we can make it even better because like this is just like average frequency, but as I said, we have sensors in the eye. And they measure things, and they are not flat. I mean, the measure response of the eye is not flat at every frequency that we can see. So I can use what is called like color matching function, more about this later, to basically compute a much better estimate of the color that we can see. And I think, let's make it bigger. I'm pretty happy with this final result. Like this looks like good color, good hue for the color of the sky. So like already just by knowing how colors come to be, you can already do all sorts of computation with them, and it's a little less mysterious how things come to be. So if we go back to the to that black body concept, then we can use the machinery that we created to compute the temperature that we perceive. The color that we perceive at different temperatures, and this is unscaled, like it's just the chromaticity. More about this later, and then we can plot this, and you see like here basically is like the temperature of this black body concept, that you have a temperature that creates like light indirectly, and at a certain point we can see that when it is like this kind of reddish here, and we can see, and raising the temperature it changes, and this is what happens, like, for example, when you have like red stars, blue stars, is basically you move across this line, and after a certain temperature it's like too bright, and again we cannot see anything. Thanks for asking. I have a slide about that. And so just to wrap this up, we have seen that like the certain temperature of light creates color, so we can simulate the temperature of light by changing color. We can do the reverse, and this is a typical image processing technique, like photography technique, that you want to change the white point of your image. So like here I put a temperature slider, and I use this function color balance to change the white of the image to go to another temperature, and I can simulate like lower temperature to have a kind of a morning or evening effect when the sun is redder, or I can simulate an overcast sky when it's like a bit colder by just by changing. And this is like only this concept of temperature applied to colors. Yeah, this is not the real sun. Yeah, of course. The shadows are all wrong, as you can see. And okay, so let's quickly go back to color numbers and how we put the. I mean, we have computed light and frequency and spectra, but we need numbers to display. So very quickly, I spoke about sensors in the eye. We have 3. I mean, we have 4. One is sensitive to just brightness, but it's not relevant to our discussion, so not about that. We have these 3 sensors. This is the response curve of a sensor. And you can see that if we look at the spectrum, one is mostly sensitive around the blue light, and the other 2 is one like around green light, and the other one peaks a little shorter than red light. So like RGB, not by chance. And so basically this is the raw data that comes in. Okay, intermission, if one of those doesn't work, you have color blindness, and it's surprisingly more common than you think. And this is like a simulation that we do with the image effect function of like how people may perceive colors when one of the receptor is damaged or absent. You have to move to a different space. You have to move to the space of color defined by these 3 functions, and then you can like inactivate or reduce one of them. And actually, this is, if you are doing an application like UX design or something like that, this is very, very important, because like 5% of male human being, they have deuteranopia. That means that they see like the middle picture, and your wonderful color palette is basically useless because you cannot distinguish like anything on the plot. So I talk about the eye, but actually we all know about like RGB. So like we need a way to display this incoming light with not so many numbers. Like we picked 3 because we have these 3 receptors. So people in the 20s started like making experiments, and so one experiment was very like foundational, was like a color matching experiment. The idea was basically, let's take a disk, split it in 2, and on one side I just put a random color, and on the other side I put a color combination. So I take like one blue light, one green light, and one red light that I will define, like specific wavelengths, monochromatic light. And then I have 3 knots, and I ask people like random people, I call people in and say, okay, look at one half, and like tune things to match the second half to the first one. So basically the idea is like, if this works, then we don't need a complicated like infinite dimensional spectrum to tell you what color is something. We can just use 3 colors, and we can make that like in relation to the human perception just by having this measure. So this was done, and these 3 functions were like the product of like, I think 7 to 8 people 7 to 10, sorry, I don't remember, were involved in this experiment. Not too many, if you think how important it is. And so they like tune things, and then everything was tabulated. And this is how you take a spectrum and you generate an RGB color, basically, according to one standard. And if you think about that, it's basically you're taking something which is in an infinite dimensional space, and you're projecting that on a three-dimensional space. Basically, this is a three-dimensional RGB space, and every color now is a point. Every color now is a point in this cube. This free coordinate going from 0 to 1. Then you have like 0, 0, 0 is black, 1, 1, 1 is white, and all sort of things. Okay, this space was a good, and they saw it and it was good, but it has problems. Like some of them, like okay, it was the 30s. People were doing computation by hand, and if you notice, like all these functions are going negative. And you can ask me, okay, how is possible? Like they were just like turning these knobs and tuning light from like no light to maximal light. So how can it go negative? Turns out, tough luck if you want to do this just by adding light. It doesn't work. So the idea was, okay, let's not throw this away because it's promising. So let's say if you cannot really match the color by tuning those three primaries, then we allow you to add a little bit of one of the three to the color to the target color that you have to match. And so we say, okay, when we do that, we say that we basically subtract this color from the matching process. So this is why all those functions are going negative. And this tells you it's impossible to match every color that we can see just by adding three lights. And this was a problem in the 30s because people were doing computation by hand and they didn't really want to have functions that could go negative. It was like, if everything turns out positive, was okay, good check. Like they didn't want this problem. Also, these three functions, they don't really mean anything. So the idea was like, let's do a transformation and create a space that suits our needs. It's artificial space, it's imaginary space, so we can have all the properties that we want. So the idea was, okay, one coordinate, we want that to simulate the brightness of a color. And that was like sort of, like it's not a given, but I don't want to get into that. Certain other like mathematical restriction, and also this positively defined thing. So the result was this XYZ space that you probably don't know, but is used everywhere when you convert colors, because it's kind of a hub space. So this space here, you can define any color, even color that you don't see. It's not restricted between 0 and 1. You can put any number here, and it will be something, not necessarily meaningful. And this is just a matrix transformation on the previous function. So the cube that we saw here, now we live in a different vector space, and it's just this kind of skewed thing. And then you can define yet another transformation, which allows me to answer the previous question, is that given that y was the central coordinate here, was picked to be the brightness, it's called luminance here, I can take that away, and the rest will tell me at fixed luminance what the color is called chromaticity. It's like blue, the cost of blue, red, yellow. So you can normalize things, project on a plane, and you get something like this, where the vertical direction is very clear, is how bright a color is. And the horizontal direction at constant brightness, you have all the different colors. So you can then project on 2D. And if you work with colors, sometimes you have seen this. This is called chromaticity diagram. These are at the boundary of the frequency that we can see, the monochromatic frequencies that we can see. And if you combine them, you get all the colors. And you can immediately see that if you pick 3 points to create your color system like a monitor, you cannot reproduce every color. That's not solvable. Like if you want 3 colors, it's a triangle, and this shape here is not a triangle. So this is you have to balance between how many colors you want to represent, how much, if you have a byte, how much steps you want to have inside of your triangle. So I mean, it's your choice how do you want to do that. And there are many choices actually out there. You can have different spaces to work with. I think now Apple is boasting some new color space for their monitors, which is richer. But yeah, it depends on your encoding, a lot of things. So okay, this is a 3D things. And but this shape is different. I subtly change reference space. So that's yet another space, because people say, okay, we have like, this is cool, like we can invent new spaces. Let's go on. I mean, we can have one space for everything, one space to fit them all. Okay, so before I move, there's one, like, why should you care about this anyway? One example to show you why. So I have this image here with two colors, and we can do something super simple. Like, let's take the mean of these colors. I'm blurring using mean filter to blur the middle area. So you see it's green, and then goes to red, but it's kind of, I mean, on my monitor it's even better, but it's kind of dark in the middle. And why is that? Because I mean, if I don't know about what space I'm working with, I don't know what's happening. And actually, when I talked about RGB, I forgot one important thing that it's very interesting, so I put it here, is like we had that y coordinate that was the brightness, but the human eye is not linear in the energy that comes in. Like basically every sensor we have, like ears, like I think pressure as well, like vision, nothing is linear because it's stupid. Like you want to see a candle in the night, and you want not to die if the sun hits you by mistake. So like you don't want a linear response. It's a very bad idea. But if we encode the brightness linearly, then we are missing out because but the way we are made, we are super sensitive to small differences in dark, but we really don't have the same fine grained perception in the highlights. So basically, colors are encoded, are compressed when you compute the RGB value. And then to show you, like I have to be quick, and to show you the difference, like this is a linear scale, and probably if this is decent, you see a big jump between black and the rest. So colors are not encoded this way. If you want to go linearly in the color space, in RGB, you move tuck, 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 tuck. What you see is something like this. You have this compression factor, which is like roughly 2.2. And now you see that, I mean, we can see nice differences in the dark. And this is the trick that is used to capture better shadows in color presentation. So okay, it may be important. But okay, back to the problem. Like we wanted to compute the mean of two colors, but we were not working in a linear space. Maybe we didn't know. But now that we know, we can do the same. Whoop, no, this is wrong. Here. Now that we know, we can compute the same thing, and now it's what you expect. Like the coloring between red and green is not like some darkish thing. And then actually, according to the space you are in, something as simple as taking the mean of two colors gives completely different result. Like you see that I'm working here in the linear space XYZ, and that's the line that connects red and green. If you go in RGB, you have this line here that goes in the dark. And if you move, for example, in the hue space, called HSB technically, you just follow this maximum saturation color here, but it's not linear at all. So I mean, this is very important when you're thinking like about numerically about colors. And well, almost over. And if you know about this, you can build your own application. Like for example, like this is something built with a front end that just uses like image apply to apply different nonlinear functions to colors. So for example, I can say, oh, the red channel, make it like high contrast, green channel as well, and blue like something like crossfading is called, like low contrast. And now you have like a different visual effect. You can simulate all sorts of like camera filters and films. And I don't know if you can see the difference, but like it can be quite dramatic, of course. Like I'm doing subtle adjustments, but like adding some nonlinearity to your color pipeline, it's a very, very, very powerful effect. So this was a very quick thing. I'm almost done, so let's try to finish. I show this space here, and I say that subtly I change representation. This is another space. It's not RGB. It's not XYZ. It's called lab. And I mention it because it's behind many functions that I wrote in color processing Mathematica. And the idea was, okay, like we had this RGB with the light. We had this XYZ, which is useful because it's linear, have all these sort of properties, and we can define other things using that, and it's good. But we need something that captures color relations in a way that is similar to how we human capture them. Like we don't think in terms of, we don't even think in terms of RGB. We think in terms of like, this color is bright, this color is dark, this color is very saturated, this color has a lot of blue in it. So the idea was like, can we find a combination, linear, non-linear, this is non-linear, that captures better what is called like perceptually the color appearance. And so the experiments, I think this is from the 60s, forgot. There was like another space was created that was a nonlinear combination of those x, y, and z values. And this is based way more on how our human eye works. Because like we have these three functions that I show you, like the three cones, the three receptors, these. But actually, this is not what goes to our brain. The eye is a very powerful sensor and does all sorts of pre-processing of what's coming in. And the pre-processing it does is very similar, I mean, very similar because it was done on purpose, to how this space is defined. So we have like these three channels in the eye. They are like combined in a channel, which is a mean of them. And this is like how bright something is. So we say one channel we define as a brightness. It's called lightness in LAB. And it's non-linear. So it's non-linear in a way similar to how our eye is non-linear. So like you cannot do linear mixing here, but if you move a step, it should be similar to what happens when you move a step in our perception. And then the other, we have three coordinates, so we need the other two. And what our eye is doing is taking differences. So basically, is typical to sensors. Like you don't want to give an absolute number. It's much better if you stay around 0. So the other two channels are defined as they are called color opponency. So it's basically one channel tells you red versus green, and the other channel tells you blue versus yellow. And this is why physiologically it's very easy to say that a blue is greener, but it's very difficult to say that the blue is yellower, because if you add yellow, you are removing blue from the same channel. So like it's not orthogonal. You cannot do that. So the idea was like, let's define a space where we capture these properties. And here I have an image, and I decompose that in these three coordinates, and you can see plotted here. So this LAB space is very nice to talk about colors, because like now the vertical component is how bright a color is. If I stay at the center here, I have a line that goes up, which are all the grayscales. And if I move to the side, I can think about cylindrical coordinates. If I move to the side, I add saturation. It's called chroma in this space. And if I move, it's a hue. So basically, in this space, like relations are way more natural to talk about. And all our color function, color distance, color metrics are defined starting at least from this space. So the idea is like, let's see what happens. Really over. Let's see what happens when I change the something like this image is very red, oversaturated. I want to reduce it. This is when I change the contrast in RGB. Contrast makes everything gray, basically. And if I increase the contrast in RGB, this is when I use the HSB, which is a transformation of RGB. So I go to grayscale, but this doesn't preserve necessarily how bright the color is. And this is using this LAB space. So ideally, if I reduce this, the perceived brightness when I move should be constant. I don't know if it shows. It's just the saturation component that is changing. So just something as simple as adjusting an image, it has very different results if you use a specific color space. And last example, very, very quickly. This is a new function we added in 12. And you say, let's see if you want to use that to operate on colors. You want to use this space to define distances. For example, we have this plot, and it's rasterized. I want to change the color, but I cannot recompute it because I don't have the data. It's just an image. So I can use this idea of like finding a good space which is perceptually close to how we see colors. To find, for example, I want to partition color close to green and color close to red. And then I measure, these are all new functions, I measure masks for this. And then what I do is I just say, like, everything is packed for you, of course, in the function. Just shift the hue, and then you get a new color. And this was the old one. So I think it's done. So thank you, and sorry for the long talk.